My dear students, in the last class we discussed the permutation. Now for symmetry cyclic notations and some theorems we have to prove, find the order of the permutations. Today's lecture we have to discuss about the even and odd permutation and the signature of the permutation. Let us begin with the definition of even and odd. A permutation that can be expressed as a product of an even number of two cycles is called as a even permutations. A permutation that can be expressed as a product of a odd number of two cycles is called a odd permutation. Very simple. We just say that, for example, we have a, suppose we have a x is equal to, you have a 1, 2, 3, 4, 5, and then we have a pi is a permutation is a 1, 3, 5, 4. So we just write is a two transposition of this, write in the transposition form. So this can be written as a 1, 4, 1, 5, 1, 3. So that means we can say that is a two cycles, that is a 1, 2, 3. So we have a, there is a 3 cycles is a then is a product of a odd number of a 2 cycles. So this means this permutation is called is a odd permutation. If we have a, suppose theta is equal to, we have a 1, 2, 4, and in this case we have to write the, this is can be written as a transposition 1, 4, 1, 2, and that clearly is equal to 2. So this is a two cycles for this permutation. So we can say that this is clearly is a even permutation. So simple, we have to all the permutations can be written, cyclic notations can be written as a two cycles form. If the two cycles are even number of two cycles called as a even permutation, odd number of two cycles is called as a odd permutations. Now we have to define next is the signature of a permutation. The signature of a permutation, pi is denoted by signature of pi and is defined as 1 if pi is a even and -1 if pi is a odd. Means we can say that if this permutation is a even permutation, the signature is equal to 1. If it is permutation is odd, then the signature is equal to -1. It's like this pi we have to written as a 1, 1, 3, 5, 4. So this is case, this is 2, this can be written as a 1, 4, 1, 5, 1, 3, and this is clearly this is equal to odd. So this may we can say that signature of this pi is equal to -1, and then we have a theta is equal to, we have a 1, 5, 3, and then this can be written as a 1, 3 and 1, 5 is a even, that in this case of a signature of a theta is equal to, we have a 1. So simple, we have to just say that if we have a signature of permutation is nothing but if we have a this permutation is a even, then signature is a 1. If a permutation is odd, then signature is equal to -1. So every transposition is an odd permutation. So every transposition is an odd permutation, and we have to write the identity is a always is a even. We say that any because you just take a permutation, E can be written as a 1 to 1. So we have a 1 2. So you have a this is 2 1, then you have a 1 2, then 2 1, and this is equal to, you have a 1 2, 1 2. So clearly this is equal to, you have a identity. So identity permutation is always written in the form of a 1 2 1 2, 1 3 1 3 1 4, or like this. So we can say that the identity permutation is even because E is equal to this. Now we have to consider this pi as a this permutation. Now we have to write the pi in the cyclic notation. This is 1 goes to 2, then we have a 2 goes to 3. So 1, so we have a 1 and 2, 2 goes to 3, 3 goes to you have 4 and 4 goes to 1, then we have to closing this. Next we start from the 5, so we have a starting from the 5, 5 goes to 6, then 6 goes to 5, then we have a cycle is completed. So this means clearly we have a cycle. Then we have to move the 7, we have a 7 goes to 8, and then 8 goes to you have a 9, and 9 goes to you have a 10, and 10 sorry 7 goes to 8, 8 goes to 9, 9 goes to 10, and 10 goes to 8. So we have to just write into a 7, 8, 9, 10, and that is equal to again is a one cyclic notation is this. So this pi can be written as a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now we have to write the two transposition of this is equal to 1 4, then 1 3, and then we have a 1 2, 1 4, 1 3, 1 2, and that is equal to, this is a, we have to counting the number, then this is already is a 2 transposition, then we have to write is a 7 10, now we have a 7 to 9, and then we have a 7 to 8. So this is total number of transposition, 2 transpositions are 7, is a product of a 7 transpositions. So this means we can say the pi is an odd permutation, and the signature of this is equal to -1. So this is very simple, we have to write into this form. We can easily calculate the, if this is a permutation is a even or permutation is a odd permutation, and then if it is even odd we can easily find the signature of such a permutation. Now consider another, we have to just say that this is, we have a 1 goes to you have a 2, 2 goes to you have a 3, and 3 again goes to 1. So you have a 1, 2, 3, there is a 1. Now we have to going to 4 goes to 5, and 5 goes to 4, then we have a 4, 5 is a permutation cyclic notation, and then we have a 7, 6 goes to 7, and 7 goes to 6. So this is again you have a 6 7, thus we have a 3 different disjoint cycles of this permutations. This is 1 2 3, then 4 5 and 6 7. We write in the transposition form. This means theta can be a product of a 4 transpositions. So theta is a even number, so it means signature of a theta is equal to 1. So in this case we have to simply we write into the form of these two signatures. Easily we have to calculate the permutation of 2 cycles, and we have to calculate the this signature also if we have a. So we just every permutation we write the cyclic notation and the disjoint cycles of a permutation, and after disjoint cycle we write into the 2 cycles, means we have a transposition of this, every 2 cycle is a transposition in the transposition form, and then count there is a transposition is a even, is a permutation is a even, transposition is odd, then we can say that the permutation is a odd. Accordingly, if the transposition even, signature is equal to 1, if transposition is odd, then signature is equal to -1. So every permutation in Sn is either even or odd, but not both. So we simply say that every permutation in Sn is a finite group where n is strictly greater than 1 is either even or odd, but not both. So we have to just prove let pi belong to Sn. We know that the transposition above the pi can be written as a product of a transpositions. So we have a this pi can be written as a a1 a2, then we have to a2l minus 1 a2l, and then same is equal to we have a b1 b2, and then we can b2k minus 1 up to b2k. Even we have to just take a is a transposition form. Now we take a pi inverse is equal to identity. So we just write a a1 a2 a2l minus 1 to b1 b2 ka inverse, and then b2 b ka inverse can be reversing the order. So this means it is a b2k minus 1 and then b2k the inverse, and then show and b1 b2 ka inverse. So if we have to writing in this form, then this a1 a2, then this is a2k 2l minus 1 a2l, and b2k minus then vk2 minus 1 inverse of this is equal to same. We have a 2 transposition, either we have to write a 1 2 or 2 1 is the same. We have a 1 2 is the same, inverse of this is equal to 2 2 1. So, this is 1 2 and 2 1, this is the same as a 1 2. So, this can be written in the sum 2k minus 1 b of 2k and then also b1 b2 in this product. So, this we have to write into this product. Now, you can see one written as a product of L plus. So, this is clearly we have to this is clearly we have L and then this is equal to K. So, we have to just say that is a as a product of L plus K transpositions, and but the identity is even. So, L plus K must be even, therefore, either K and L are both even or both are odd. Now, we know that the if L plus K is equal to even is only possible when L and K are both are even and all both are odd. So, this means we can say the identity permutation is always even, we know that. So, by the identity permutation we can say that simply say that L plus K is even only when both L and K are even or both L and K are odd. So, we cannot say that one is even, one is odd. So, this means either clearly we can say that either the even permutation is even or odd, not both. So, now for example, we have to just discuss this example. Let pi is equal to 1 2 3 4 5 6 7 and this is clearly a disjoint cycle of at 7 is pi is even or odd and why. So, we just write the two transposition of this. Clearly, this can be written as a 1 3 1 2. Now, we have a 4 7 4 6 and now we have 4 5. Now, we have a this is equal to 1, this is 2 3 4 5. So, number of a transposition in this case we have a clearly is a 5. So, 5 is an odd. So, we can say that this is a permutation pi is equal to pi is a product of a 3 cycles even and 4 cycles odd. So, this is a even cycle and this is a odd cycle and it is odd. So, we can just say that if we have a this is even cycle, this is odd cycle, that means we have a 3 is even, 4 is odd, then this product of this is equal to even plus odd. So, is equal to odd. So, this means it is clearly alternatively we can say that we have to just say that this 1 2 1 this is written in the form where not there are an odd number of them. The shortest decomposition will be a 5 transposition and then we can say that clearly this is a permutation is a as an odd permutation, and if it is odd permutation then the signature of this pi is equal to minus 1. So, we have considered this is signature of a pi is equal to minus 1. So, this is clearly we see this clearly this is we have to just take a decompose this into the 2 cycles, or by the theorem we can say that either even or odd. So, this is a clearly this is a odd order is a 3 cycles. So, is a product of a 3 cycles means is a even if we write into this, and this is a even is a 4 cycle. This 4 cycle is always is an odd. So, if 2 permutations are coming in the odd, so we can say that if we have a this is even plus odd, then we have a total is a odd again. So, we have to just say that clearly this is a odd permutation. So, we can quickly determine whether a permutation is even or odd by examining its cyclic structure. First, notice that an M cycle can be written as a product of M minus 1 transposition. If we have a clearly we just say that the M cycles and we have to just write for example 1 3 5, this is 3 cycles. Now, we can write as a 1 5 and 1 3. So, every M cycles can be written as a product of a M minus 1 transposition. If we have a any permutation which is M cycles, then this M cycles can be written as a M minus 1 2 cycles or M minus 1 transposition. Therefore, cycles of a even length corresponding to the odd permutations, while the cycles of a odd length corresponding to the even permutation. So, means if we have a cycle of a even length corresponding to the odd permutation. This is we have a and the cycles of a odd length corresponding to the even permutations. For example, 3 cycle, this is an even permutation. So we have just say that this is 3 cycle, or 3 cycle is an even permutation. The cycle is of odd length corresponding to the even permutation. A cycle of a even length, if we take a 1, 3, 5, 2, and this is clearly we have a even length, and if we take write a transposition is a 1, 2, 1, 5, 1, 3, and then you have to just take that is a odd number. So this is m is equal to 4, 4 minus 1 is equal to 3. So this is odd. So if we have m cycles, can be written as a product of m minus 1 transposition. If m is we have to just say that even cycle, then we have a odd transposition. If we have a odd length of a cycle, then we have a even permutation, even transposition we have to getting, and then we getting the permutation should be the even by the definition of a permutation. So that means we can say that this result, an m cycle is even if and only if m is odd. M cycle is even if and only if m is a odd. So if it's m, then we have a cycles, m cycle is a even, we have to prove this. If m is equal to 1, then we know the identity is always even. So if m cycle is m is equal to 1, then the identity is clearly is a even. So if m is equal to odd, m is equal to 1, then we say that the identity permutation, and then this clearly m is equal to even. Now if m greater than 1, then by the theorem we just say that by this theorem, if n greater than equal to 2, then any permutation pi belong to S can be expressed as a product of a transposition. While we note that m cycle as a product of a m cycle can be written as a product of a m minus 1 transpositions. So this means this pi and Sn expresses product of transposition, and m cycle as a product of a m minus 1 transposition. So the disjoint cycle decomposition of a permutation allow us to determine whether it is even or odd. So the preceding theorem show that whether each this completes the proof if m is equal to greater than 1, then we can say that m minus 1 transposition. So if m is a even, m is equal to odd, then m minus 1 is equal to even. So we can say simply into this form. The disjoint cycles decomposition of permutation allows us to determine whether it is even or odd. The preceding theorem we have to just shows whether each cycle is a product of an odd or even number of transposition, and we have easily decided the parity of the entire permutation. So we have to by this we can easily discuss enable us to easily decide the entire parity of the entire permutations. Next we observe that pi can be written as a product of a m transposition, and theta can be expressed as a k transformation. Then theta and pi can be written as a m plus k transposition. For example, very simple example, if we have to take a pi is equal to 1, 2, 3, then as 3 we have to take is equal to 3, 1, 2, and we have a theta is equal to, we have a 1, 2, 3, then we have a we write into the form of a this is equal to 2, 1, 3. So this is clearly we write is a this is the cyclic notation. If we write 1 goes to 2, 2 goes to 3, 1 to 3, then 1 goes to sorry, this is not, this is we write pi in the cyclic notation in the form of a 1, 3, 2, and this is 1, 2, only 1, 2, and this should be, I just change, I just write this is equal to 3, 2, 1. So this can be written in the form of a, we write in the form of a 1, 2, and 3. So this is, we have a right in the theta and pi. We can calculate the suppose we have to calculating the pi theta. So we have a pi theta is equal to 1 2 3, then theta 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 2, and then this is equal to 3. This is equal to, you have a identity, and this is clearly you have to just write. If we say that if we have to write in the observe that this can be written as a pi can be written as a product of a m transposition, and theta can be expressed as a product of a k transposition. So this is written as a 1 2 1 3, and this is written as a 1 3 1 2, and then you have to this is a 2 transposition, this is a 2 transposition, and this clearly m plus written as a product of m plus k transposition, recalling that the even plus even is a even, odd plus odd is a even, and even plus odd is odd. We obtain the following properties of a permutations. By using this, we can say that simply we have to using this the product of two permutation is always even, is a product of a two even permutation is even, product of a two odd permutation is even, product of an even and odd permutation and vice versa is a odd, if we have to just say that. And now moreover, if theta pi can be written as a theta product of a this transposition, and then pi inverse can be written as a theta n minus 1 theta 2, transportation is this then we have a pi inverse is equal to identity. Then the following we have the inverse of an even permutation is even, if inverse of an even permutation is even. For example, if we have to write 1 3 5, so you have a 1 5 and 1 3, and that is clearly you have a even. If you write is a 5 3 2, then 5 3 1, so we have a 5 1 and 5 3, that is equal to you have a pi, and then this is equal to you have a pi inverse, and this means we can simply say the inverse of an even permutation is even, and the inverse of an odd permutation is also odd. If we take a pi is equal to, we have to take a 1 5 4 3, then we have to permutation is equal to, we have a 1 3 1 4 1 5, and clearly this is a odd. Now we can find a pi inverse. This can be written as a 3 4 5 1, and this can be written as a 3 1 3 5 and 3 4, and that is again is odd. So we can clearly say that if we have a inverse of an even permutation is even, and the inverse of an odd permutation is odd. Let S9, we have to just say that S9 pi is equal to, this is clearly is a disjoint, and this is even because 1 2 3 is a 3 cycle and is even, product of a 2 transportation, and this is 4 5 is a 2 cycle is odd. So we have a 1 transposition, and then you have a this is again is odd, 4 cycle and is odd, the product of a 3 transpositions. Clearly, just if you want, we can just write in the form of a 1 3 1 2, and this can be written as a 6 9 6 8 6 7. So this is the nothing but is equal to even, odd and odd. So we have a this even plus odd is equal to odd, odd plus odd is equal to even. So this is even plus odd is equal to even. So this means this by this we can easily identify the permutation is even or odd. We simply write in the form of this is 3 cycle. The 3 cycle is odd cycle is always is a even, and this is a even cycle. This is 2 cycles already, and this is a 1 transposition is odd, and this is a and this is equal to 4, and 4 is always giving you the odd. So 4 cycles is always giving to 4 minus 1 is equal to 3 transpositions. So this means odd number of odd transpositions, and so by this we can say that even plus this is even, and this is plus odd, and this is plus odd, and that is giving you a completely is equal to even transposition. Alternatively, we can just, if we write into this form, we write in the form of a 1 3 1 2 4 5 6 9 6 8 and 6 7, and now you have to just counting this is equal to, you have a 6. So this means 6 is a clearly is a product of a 6 transpositions, and 6 is even. So this pi of in S9 is clearly is a even permutation, and then signature of this pi is equal to 1. Now we just say that two permutations pi and gamma are said to be conjugate if there exists a permutation theta such that theta pi theta inverse is equal to gamma. If we have a two permutation, and then if another permutation is exists, uh, means theta pi theta inverse giving the this another permutation gamma, then we can say that simply is a this pi and gamma are conjugate to each other. It is easy to see that being conjugate is an equivalence relation, and the corresponding equivalence classes are called the conjugacy classes, and therefore this gamma is equal to theta pi theta inverse is equal to gamma for some theta belongs to Sn. For only reason why conjugate is so important is that it measures how far the group G is form being an abelian. Indeed, if G were abelian, then we have a theta pi is equal to pi theta, and then you see this, if multiplied by theta on the right hand side, we have a theta pi theta inverse is equal to pi. Thus G is abelian if and only if conjugate of every element by another element equal to element itself. So if we have to just this, we can say that this means conjugate of every element by another element equal to the element itself. We have to giving the pi into itself. So there exists some element theta belong to the Sn, then theta pi theta inverse is equal to pi, then we have to say that simply is this, then G is abelian if and only if condition is hold. If G is abelian, then the conjugacy element itself, its conjugacy element equal to element itself, then we can easily prove by this. So other way we can just say theta pi theta inverse is equal to pi, then we have to just say theta pi theta inverse, and theta is equal to pi of theta, and then we using the associativity theta pi theta inverse theta is equal to pi of theta, then you have a theta of a pi, then this is equal to, you have a identity is equal to pi of theta, and this can be written as a theta of pi is equal to pi of theta. So we can simply say that this conjugacy is so important is that to measure how far group G being an being abelian group. So we have this theorem is saying that if let pi is equal to a1 a2 ak be k cycles in Sn, and theta be any permutation belongs to the Sn, then theta pi theta inverse can be written in the form of a theta a1 theta a2 up to theta ak. So we just proof we have to write, take a pi and theta belong to Sn, pi is equal to into this, then theta pi theta inverse theta of ai, and this is nothing but is equal to theta of a pi of ai, because we have a theta pi, then we can write as a theta inverse theta of a of I, and then this is equal to identity. So we have a theta pi of identity of a ai, and this can be theta pi of ai. And now for all I except I is equal to k, if I is equal to k, which the case is equal to theta pi ak is equal to, we have a is equal to going back to the original. So we have we know that the theta pi of ak is equal to a1. So this is theta of pi of ak is equal to theta of a1. Therefore this theta pi theta inverse describes the mapping theta a to a1 to this is a1 to theta a2 and so on up to the theta ak, and then again going to the back to this is theta of a1. So pi theta a inverse is the same as a theta a1 theta a2 up to theta ak. So this means this we have to describe the mapping into this. If you can theta of a1, then you have to again rotating this. So we have all the values of k minus up to k. This is theta of ak, and then we have to again theta of ak is giving to a going to back to the value of a1. So in this case we can simply say that this theta pi theta inverse can be written in the theta a1, theta a2 and theta ak. Now next theorem we have to prove two permutations pi and gamma are conjugate if and only if they have the same cycle length. So we can just say that the two permutations are the only if and only if they have the same length. So proof by the this previous theorem, two permutations are conjugate, then they are the same length. We have to just say that by this, because we have to this pi is equal to ak is this, and then theta, and this is equal to this another, this again the length of a k. So by the this theorem, if two permutation are conjugate, they are the of the same length. Now conversely, if we have a both the permutation are the same length, then they are conjugate. So conversely, if two permutation pi and gamma have the same cycle type, then simply choose a theta belong to Sn such that theta of pi theta pi I is equal to gamma of I for all I belongs to 1 to n. Then conjugation of by theta, we can have theta pi theta inverse can be written in the form of a theta pi 1 theta pi 2 and so on theta of pi n, and this is nothing but is equal to, because of this can be written in the form of this. So this is nothing but gamma 1 gamma 2 and gamma n, and then gamma 1 pi and gamma having equal cycle length and necessary and sufficient condition for their conjugacy. So we have to just say simply we write into this form, and if we write into this form theta pi theta inverse, so we just say that by the previous theorem this can be theta of pi 1 theta pi 2 and so on, and that is the n length, and this is also the for all n length. So we can say that theta and gamma pi and gamma are the pi and gamma having equal cycle types is necessary and sufficient for their conjugacy. Okay, so now we have to just to compute the conjugate of a pi by theta, simply translate the elements of the cycle decomposition of a pi. For example, suppose we have a pi is equal to this in S8. Now we have to theta is equal to, we have to in the form of this 1 3 5 8 7 6 7, and now then the conjugate of a pi by theta is theta pi theta inverse. So we can say that theta pi theta inverse. So we have to take a first is a theta inverse. So theta inverse can be written in the form of a 4 8 5 3 1, and then we have a 7 6 7 6 the same as a 6 7, and then we have to operate the pi, and then we operate by theta again. So we just in 8 we have to simplify into this form. For example, just we starting from the 1 for theta is 1 goes to, you have a 4, and then if you go to the over 4 is goes to, you have a simply is equal to 2, and then again we have to coming here, then 2 goes to, you have a 2, so 1 goes to 2. Now we have to starting from the 2, and then is here is a theta inverse 2 goes to 2, then we have to move to the here 2 goes to 2, and then here the 2 goes to, we have a we have to, this means we have a clearly here we have to just say that So 1 goes to 2. So now we have to start from the 2, then 2 is not here. So this means clearly 2 goes to, in this cycle 2 goes to 2, and 2 goes to 2 means we have to going to 2 goes to 3, and in this cycle again theta goes to, you have a 5, theta 3, sorry, I am sorry, this clearly we have to just say that in this 2 goes to theta inverse 2 goes to 2, and then we have to go to the pi, and 2 goes to is equal to 3, and now is 3 goes to 5. So this is equal to, clearly goes to 5. Now we have to 5 goes to, you have a 3, and then you have a 3 goes to 5, and then you have a, in this goes to 5 goes to, you have a, we have to start 2 5, and then 5 goes to, you have a 3, and then 3 goes to, you have a 5, and 5 goes to, you have a 1. So this means we can simply in this way we can write in the form of a we just take a 5 goes to 3, and then we have a 3 goes to 7, and 7 goes to 6. So we have a, this is equal to 6. Now here is a 6 goes to, you have a, clearly is a 7, and by this 7 goes to, you have a 4, and then is 4 goes to, you have a 1. So this means this is clearly 1 2 5 6. Yes, you can write as a 5 6 1 2. Clearly one cycle is this. Now we have to starting again by the 3. Now the 3 is going to 1, then we have to go to the 3 goes to 1, then 1 goes to, you have a 6, then you have a 6 goes to 7. So 3 goes to, you have a 7. Now again this composition 7 goes to 6, and now 6 goes to, you have a 5, and then 5 goes to, you have a 8. So this is going to 8. Now 8 goes to, you have a 5, and then you have 5 goes to, you have a 1, and then you have a 1 goes to, you have a 3. So you have a 3, then we can say that simply is equal to 3 7 8 is a another composition. This so this means this theta pi theta inverse can be written to a this disjoint cycles of a. Now I stop today lecture here, and we continue some examples and some more problems into the next lecture of this permutations class. Thank you.